Sweet. So I'm going to go ahead and get started. If we have more people come in, I know Molgen is probably holding some people over right now. Did you guys have Molgen all the way up? Oh, well, that's awesome. Never mind. Cool. So this sheet that I have for you all is not a all-inclusive review sheet. I just wanted to cover some stuff that I thought were important and that people seem to be missing as far as what lecture goes and what I've been seeing on the homeworks. So for this first part, we're going to go over some different equations together and show what's really easy to figure out based on what's given to you in the problem, and give you some definitions that you can use and keywords that you can pull out from different problems to help make things smoother. And then below that, I have state functions and intensive and extensive properties. There's still some people that don't quite get that, so I want to highlight that a little bit. And then I have two problems that are at the bottom that I'm going to have you guys work together to figure out for a little bit, and then we're going to do them as a group. And most of them have to do with delta G and with mu, which we just recently learned about, but could very possibly be on the exam. So I wanted to drive those in a little bit and give you some experience with some word problems with that. First off, any questions that you all have? No? Yeah?
Oh, the problem set? One of the questions is just like, you know, how many points you know.
Yep.
When you say in class, do you mean like based on in class, or not more
Right. So for that, I'm explicitly looking for what Dr. Cohen has given in class. So not supplemented by the book, just what Dr. Cohen has provided during class. I believe there's about 4 that I counted. So yeah. Yeah.
What time do you have problems that turned in by tomorrow?
So I will not be here all day tomorrow. If you turn it in sometime tomorrow, it will be fine. It is down in the front office, and Stacy has the box right next to her desk. Yeah. Any other questions for that? Cool. Yeah. Is there not any more back there? Crap, more of you showed up than I thought. Can you share with somebody and I'll print it in a minute? Yeah, sweet.
The follow-up is that since you're not here tomorrow, you
Yes.
still have recitation, correct?
We do not have recitation tomorrow. Do not show up to Clark or physiology, psychology, whatever that building is.
Pathology.
That one, pathology. Don't show up to either of those buildings. I will not be there and you will be sitting by yourself. Any other questions? Okay, cool. So let's dive into this a little bit. When we get to the bottom part where we start doing equations, I'll print out extra ones for those of you that didn't quite get them, but we'll get to that. Okay, cool. So going over some equations, I'm going to ask for a lot of feedback in this, so please be vocal. So what is something that is always true that we have learned so far? It's one of the basic ones. It's one that you guys are the most comfortable with based on previous classes. What's the equation that we have?
Delta U equals delta W equals delta Q.
Sure. Okay. Perfect. What's another one?
Delta G equals delta H minus T delta S.
Yes. Yes. What else?
Q equals T times delta S.
That's not always true. So this is the always true part. How about gases? Okay, very good. Cool. And then there are some that have to do with heat capacity. So Q to T, very good. And then delta H is equal to Cp delta T. And oops. And right. So these equations are always true. No matter what is going on, these equations work in any system that you're looking at. We good with that? Okay. Next one. What are some stuff that only works at constant pressure?
Constant pressure.
it is, but CP can be applied to something else at constant pressure. What does delta H equal at constant pressure?
Debbie.
Q. So what does Q equal at constant pressure?
U plus P.
Okay, very good. And then at constant pressure, we also get that delta H is equal to delta U plus P delta V. Right. Cool. Everyone good with those? Sweet. Okay, next we're going to move to constant volume. What is always true at constant volume? Anybody? What is delta U equal to at constant volume? Yeah. It's also equal to Q. So this is constant volume. So at constant volume, Q is equal to delta U. At constant pressure, delta H is equal to Q. Good with that? So this is where we can sub in the heat capacity at volume for Q, and then we can do heat capacity at pressure when we're at constant pressure. Does that make sense to everyone? Okay. Next one we got, what is work at constant volume? Yeah? Perfect. What is delta H at constant pressure? Yep. Plus? Oh, no, that's it. Sorry. Very good. Yep. Okay. And then one that we haven't dealt with a whole lot because we don't really work in constant volume a whole lot in biology, but what would delta A be equal to? He briefly mentioned this in class. So,
W plus. Yeah.
cool. Everyone? Yeah.
What is A?
A is, it's another way of expressing Gibbs free energy, but instead of doing it at constant pressure, you do it at constant volume. Cool. Any other questions with that? We probably won't have any questions with that because, again, biochemists and biologists and chemists typically don't work at constant volume. Okay. Next one. For a reversible process, what is true?
Q reverse is equal to T delta.
Right. Cool. That's really the only thing that you get from reversible. So if you have a reversible system, remember that you can relate entropy to heat and go from there. Usually that's a pretty big indicator if they say reversible on a system. Okay. How about an irreversible system? What would work equal? You all loved this on your homework. Most of you got it wrong.
It's the negative P external.
Right. So one thing to point out, P external has to be explicitly given to you. If they say that the final pressure of a cylinder is equal to something, that does not necessarily mean that that is atmospheric pressure. So you cannot assume that P external is equal to your final piston pressure. Okay? Cool. Next one, for an irreversible process, what could delta S be equal to? This was also used on your homework, but later on part of it. You can use that, yep. I would recommend using this one. And that will be for an irreversible system as well. Okay. Next thing is an isothermal system. So when we have an isothermal system, there's something that immediately goes to zero. What would that be? Delta U, yeah. Okay, and then Q would be equal to what in this case? Negative W. Right. And then we also get that delta S is equal to NR ln of VF over VI. So that applies to both a irreversible system and an isothermal system. Do all of those equations make sense to everyone? Okay, cool. So those big ones that I pointed out, the big 6 that are underlined, are things that you should really look for in a question that is called out. So be that on your homework or the exam. Try to look for those keywords and figure out what equations you can use for that problem. Cool? Okay, next one. Let's list some intensive properties. Okay, shout them out.
Density.
Density. Temp. Pressure.
Molarity.
Yeah. What else? How about molar weight? And heat capacity. Cool. Okay, now thinking about extensive properties. What do you all have for some of those? Entropy.
Volume, energy, gas.
Yeah. Mhm. How about heat? Most of you got that on problem set 1, but the heat is directly related to how many moles you have. So if you have half the number of moles, then you can just divide the heat by half. So that's an important one to know. Okay, cool. So if you could find 2 people around you, so working groups of 3, and work on that first problem. I'll give you guys 5 minutes and then I'll work. Okay, cool. Let's bring this back together. So, first thing, what is the chemical potential of this reaction? 5 kilojoules. So is that positive or negative?
Positive.
So what does that mean for delta G?
That's not a bump.
Right. Okay, so what equation can you use to solve for the C value that you're looking for? We learned about it today in class.
That's mu equals RT ln C2 over C1.
Okay, and then you were given a concentration of 200 micromolar. Millimolar, sorry, I wrote millimolar. Okay, so would that be C1 or C2?
C1.
Would it?
C2.
It is C2. Can someone explain to me why it's C2?
Delta G is positive.
There's a lot of mumbling, but I heard right answers. So the way that I think about it is that in order for this to be positive, we had to have a positive number come out of our natural log. So that means that our bigger number had to be on top, because if you take the natural log of a large number, you get positive. If you take the natural log of a fraction, you get a negative. So that's why this is equal to C2. So going from that, what would C1 be equal to?
What did you work backwards?
Did anyone solve for it?
Oh, yeah, 25.68 millimolar.
Yeah. Okay. Does everyone know how to rewrite this equation? I saw no's. So, okay. We have delta U, or mu, is equal to RT ln of C2 over C1. First thing you do is divide both sides, so by RT, and we get delta mu over RT equals the ln of C2 over C1. Next, what you're going to do is take the exponential. So we get e raised to the delta mu over RT is equal to C2 over C1. And we're looking for C1, so this is going to be C1 is equal to C2 divided by e raised to the delta mu over RT. Or if you have a TID9, just use the solve function. Cool, does that make sense?
So you said that you need to have, which this makes sense, that you need to have the large number on top of the positive number.
Right.
But how did you know that your 200 is necessarily your?
Because it
largest
said
number?
that it was from a high concentration.
Okay, okay.
Yeah.
G is positive. Both.
Yeah, that I got, but I wasn't sure.
Yeah, you just
Multiply the 5 by 1,000, and then you're doing this, or can you still?
say that one more time.
You multiply the 5 by 1,000?
Yes, yes. You should, for a basis rule, you should always work in joules. If it gives it to you in kilojoules, convert it to joules because it is much easier to use that, and R is usually defined in joules, and so you're going to have a much better time. Yeah.
R in this case is Avogadro's number?
No, R is going to be equal to, I think it's 8.314. Yeah. Any other questions? Okay, cool. So I have been asked to go over 10.3 of this current homework. How many of you have been having trouble with that? Okay. Oh, and for those of you that haven't started yet, I recommend it. It's a long one. Okay, cool. 10.3. So what we're being asked is to prove that delta mu is negative. We're also wanting to show that delta G is negative. And you need to go about proving this through mathematical equations that the two are both equal to each other and both negative when this happens. So, the first thing that we're going to look at is what Dr. Cohen showed today in class, which is that mu is equal to delta G divided by delta P at constant temperature and volume. Pressure, sorry. That's also wrong. N. Okay. Have you all seen this before in your physics classes as at constant? Okay, fun fact, this means at constant. Cool. You'll probably see it a lot more in the PChem book. They use it a lot for deriving a bunch of equations. Yes, it is in the book. Okay, cool. And then thinking about delta G, what's our favorite delta G equation? Yeah, delta H minus T delta S. You can't jump there yet, Idris. You have to prove that it gets there.
What's that M? That was a tag. You're it. You're it.
Yes. Okay, cool. So breaking this down further, what can we break down delta H into?
Or delta U.
Okay, so remember from earlier, at the top of our equation sheet, we had delta H is equal to delta U plus P delta V. Okay, what can we break down delta U into? Yeah. Okay, what can we break down Q into?
T delta S.
Okay, what can we break down work into?
P delta
The
V.
external temp plus.
And delta mu times delta N.
Right. So some of you might have found this in the book. There are multiple things that work can be equivalent to. The work that we've been working with is super generalized. So we've been working with P external times delta V. This is the biggest component that contributes to W or work, but there are, I believe, 5 or 6 different things that can actually contribute to work. We just ignore them most of the time because they're usually negligible. In this case, it's not negligible. So we include mu delta N in this place. Okay, so now we're gonna go ahead and basically funnel all of this up back to our delta G equation. And what does that come out to simplified?
Delta G equals U delta.
Right. Cool. So the next part, we proved that delta G and delta U are related to each other. That's the first step. The next step is that we have to prove that when mu is negative, delta G is negative. So how would we go about proving that mu is negative?
Delta mu equals RT ln C2 over C1.
Okay, so given the problem that we had, was C2 or C1 larger? C1 was larger. So that makes the ln what? Yep. Which makes mu negative, which makes delta G negative. Does that make sense to everyone? This is how you go about proving that it works. There are other ways of doing it. I've seen some homework turned in already that proved it a different way. And if you go about doing it a different way, that is fine. But this is the way that I've done it, and it's easy. Cool. Any questions with that? Another question that I've gotten with this is, would you be expected to do this on an exam? In previous years, each exam had a proof. That might not necessarily be the case this year. Dr. Cohen is completely a different professor than has taught in the past, so I'm not sure. But it has been asked in the past and is fair game to ask to prove an equation. Cool?